Okay, we'll talk about the final and everything else, which is going to take place on Thursday. We'll talk about that towards the end. What we're going to do is this will be the last set of material that'll be on the exam. We're starting Chapter 9, and Chapter 9 is titled Parametric Equations. And polar coordinates. These are two separate topics, and we'll start with parametric equations. I'm gonna turn my phone down. I'm expecting an important phone call from my daughter's doctor. So if you hear my phone ring, I'm probably just gonna like run out real quick and answer it in the hall, okay? Put that here. Okay, so two different types of, or two different topics here. We start with the parametric equations. So parametric equations, have any of you ever done anything with parametric equations? Does it sound like something you've seen, perhaps? A couple of you, okay. I really like this topic, and here's why. If we go back to the idea of a function, you know, what is a function? And if you remember, like in a college algebra class, they gave you this definition of a function, and it had some weird wording in it that we had to be very particular about. And then there was a more like general definition that you could say, like in layman's terms, just tell someone, okay, a function is like a machine. It maps a number to a number, but it's more than that. And so I want to write kind of a loose definition of what it meant to be a function. A function is a rule which assigns to each element x in its domain exactly one element which we often called f of x or y. And that's pretty much it. And the key to it is that it was exactly one element. So in a picture of what a function was doing is we had this thing over here which we called its domain. And most of the functions that we study in a calculus class and college algebra class, this domain is just numbers, right? So we say, like, I'll put double struck R to mean that the domain is coming from real numbers. You're going to take a real number in, plug it into a function, so maybe the x is some value here, and then it gets mapped over through this function into some set of numbers over here, which we call the range. Sometimes that's also called the codomain, but college algebra, they usually call it a range. And that range also consists of numbers. And that's what we've seen. And so that point that it goes to over here, we'll just call it y, was also a number. So you take a number, you map it to a new number, that's what a function is. The fact that it says that it goes to exactly one element means that you could not have this happen. You could not have one element go to, I'll call this one y sub 2. You could not have x go to both y and another place, y sub 2. So you couldn't have it go to two places. If it did that, then it was no longer a function, right? We would say this would not be a function of x because it takes one element and maps it to two, right? That makes sense? That look kind of familiar? All right, so with that in mind, if we take something as simple as a circle, so let's take an example. You take a circle, this is our x, this is our y. Let's just center this thing at the origin. It's a terrible circle. Okay. Let's say that this thing has a radius of r. Then if I want to draw that circle with a function, the problem is I can't, because the function would fail the vertical, we would fail vertical line test here, wouldn't we? So this circle is not representative of a true function. But circles are something we want to be able to deal with. In fact, we want to be able to deal with a lot of functions or a lot of relationships where they fail the vertical line test. I mean, what if you have something like almost looks kind of like a teardrop sort of shape, maybe like the airfoil of a wing or something, like cross-section of the side of a wing? That again would fail to be a function, but it's something we want to be able to study, right? So is there a way to get around this whole idea of vertical line test and failing to be a function? And that's where parametric equations come in. What we do is to draw a circle. We'll stick with the circle just because it'll be the easiest to work with. Is instead of looking at a function that takes in a number and spits out a number, right, like the one above took a number in. I'll write it up here. This right here, it takes a number in and it spits a single number out, right? That's what happens with that function. Number in, number out. Get rid of that first arrow. Instead, what we're going to do is we're going to take a number in and we're going to spit out something in two-dimensional space. So we're going to take something in, our input, and spit out a point in the plane. So our input will be a number, but our output will be a point, an x and a y, and it'll be a point. Now, there's nothing that says you can't have a function that takes in a number and spits out an ordered pair, right? It just, to be a function, it has to follow the fact that for each input, there needs to be exactly one ordered pair, right? That's what we need to happen. You can't have the same input go to two different ordered pairs. So that means that if I'm going to try and draw a circle, every single point on the circle has some x and some y coordinate, correct? Every point. And what I want to do is be able to plot each one of those points by plugging in some number. And that number is no longer going to be on our picture. Like up here, the input, x, we graphed it, didn't we? We said x is how far you go to the right, y is then how much, the output is how high you go. This time, the input that we're going to actually have is not going to be in our picture. The only thing that we're actually going to draw is the output. The input is going to be almost like time running in the background. So we like to use the variable t as our parameter. Okay, our parameter is going to be t. So to kind of add to this picture here on the right, what we're going to do is we're going to take t as an input. Again, t is a number. And then from that, it's going to spit out an ordered pair. Now, we know that it's got to spit out this point. This is going to be an x and this is going to be a y. But the actual x value will depend on what I plugged in, and the y value will depend on what I plugged in also. So instead of writing x and y, we write x of t and y of t. In other words, the x coordinate of the point is a function of t, and the y coordinate is a function of t. These two functions of t do not have to be the same functions. If I do it this way, watch, we can draw a circle and still do it maintaining what a function is, all right, maintaining the definition. So can someone tell me for this circle with radius r, how I could somehow connect the x coordinate and y coordinate to something? Remember from pre-cal, if you have a point on the circle, right, and you have a fixed radius r, then the only thing that you really need to know in order to determine where you are on the circle is what? If you know that you have to walk out a distance of r, then how would you know what point you're at? What's the only thing that's dictating where you are in the circle? The angle, right? The angle? So why don't we use our parameter, our t, as being the measurement of this angle? If that is the measurement of this angle, then I think we can all agree, hopefully, if you draw a right triangle, that x and y are these. And so what's the relationship we have? We know r is fixed. We know t is our parameter. So can you write down x in terms of r and t? So what's the relationship? T is, or what trig function connects the adjacent and then the hypotenuse to the angle? Cosine, right? So we know that cosine of t equals what, x over r? So r cosine t is x. Remember, r is fixed, right? R is a constant here. It's, I could have put 2 or something like that. And similarly, what's y? R sine t. R sine t is y. So these two equations are equations that depend on t, right? This x depends on t. This y depends on t. And what we were saying was to use this t as our parameter, that we needed to somehow figure out how the x was determined and how the y was determined. And here we're telling ourselves how it's determined, right? So this x is actually our x of t, and our y is our y of t. And these two equations right here are called our parametric equations. So the parametric equations for a circle radius r are the following. X of t equals r cosine t, and y of t equals r sine t. Now, let's just check to see that this still is a function. Because remember, the reason why it originally failed the vertical line test, right, or the reason why it wasn't a function initially, was because on a circle right here, if you don't do the parametric equations and you try and do this with just a function of x, then when I plug a certain x value in, it would have to have had two outputs, right? The one on the top and the bottom. I'm going to try and show you that these 2 points here and here in our representation come from completely different inputs. And as long as they come from different inputs, it doesn't matter, right? You don't have one input going to 2 outputs. So what we'll do is we'll do kind of like a t-table just to verify this. This is like old school, the way we used to do things, like at first graphing things. Over here, x, t, y of t. So your input is a number, your output's a point. And then over here, we're going to draw it. All right, so let's start with a common, starting place for t. How about 0, right? So we plug in 0. We're going to do cosine r cosine 0 r sine 0. Y'all following me? Yeah? What's cosine of 0? 1. What's sine of 0? 0. So you're going to r times 1, which is r. and you get sine of 0, 0. It's going to kill everything off. So that means that you want to plot the point R0, which means you walk out to the right R, and you put a point there. All right, let's pick another value of t. And let's keep in mind that t is an angle, right? T is an angle. So if t is an angle, I mean, in this case, it's an angle because of the way we came up with it, right, from the picture. So let's pick an angle we actually know the value of, right, for sine and cosine. So how about maybe pi over 4? Do pi over 4? So if we do pi over 4, you're going to have r cosine pi over 4. R sine pi over 4, which will give you cosine pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. So you're going to get something like root 2 over 2r, root 2 over 2r. And the square root of 2 over 2 times r, if you were to measure that, it would come up and over. It would be somewhere around here. And then if you continue this, all right, you're going to draw the dots all the way around like this. And if you filled in all the values in between, you would get your circle. Do you believe that? That makes sense to you that it would do that? Yeah. So why do we not care about the vertical line test anymore? Tell me about these 2 points. Do they come from the same t? No. See, this point comes when t was what? Pi over 4, right? Here t was pi over 4. And this one would come when t was what? 7 pi over 4. And since they come from 2 different places, you don't have the same input going to 2 different outputs. Now, what happens when I get to 2 pi? What do we get when we get to 2 pi, which is all the way around? We're going to get our original point again, right? R0? Is that okay? Is that going to violate being a function? No, because look, 2 pi goes to one place, right? The fact that it goes to the same place that 0 went to doesn't make it not be a function, right? So even with the function, you can have, the simplest example would be a constant function. Back in the day when we have f of x equals, let's say, 5, if you look at the picture of the domain and the range, here's 5, right? Every point in here goes to the same point, right? And that is a function. That's okay. What you couldn't have is one point going to multiple places here. So the fact that 2 different points go to the same place does not violate being a function. And that same holds here. The fact that 0 and 2 pi give you the same ordered pair doesn't affect the fact that it's still a function. And that is a great thing, because if we have a way of drawing things that traditionally failed the vertical line test and using functions to do it, then we should be able to also do calculus with this. We should be able to find slopes of tangent lines like we did in Cal 1, right? We should possibly be able to find the length of this curve. We should possibly be able to find areas. I mean, everything should extend somehow, some way, right? But we first have to understand this is a new type of way of drawing things and graphing relationships, all right? Y'all kind of with me on this? Okay, so let's do another example. Let's try to convert this function into parametric equations. And I'll point out, first of all, that f of x equals x squared is a parabola, and it is a function, right? We don't have any problems with this like we did with the circle, yes? But I'm going to show you right now what I'm going to show you now is that everything that we've ever done could always have been converted over to a parametric equation. You could have always done it. So let's see here. As a picture right now, what we have is that the x goes in, right, and y comes out. That's what's happening right now. We're squaring it, right? X squared goes through whatever. You get your y. What I need to do is somehow convert this over into something that looks like this. T goes in, and then an ordered pair comes out, right? X, y. Do you agree? So tell me about, in this blue scenario where it's a traditional function, when we draw it, tell me about one of these points. Can you tell me what the coordinates of that point are? What's the x coordinate? What's the x coordinate of that point? Okay, if I plugged in 1, then, right, it would be 1, and then the y value would be 1 squared, which would be 1, right? What if the x coordinate was 2? What would the y value be? 4. If it was 3, it would be 9, right? So what if the x coordinate is x? What's the y value? X squared. Do you agree? The x is the x coordinate. The y is the x squared. And can you look at both of these as functions of a single variable t? This is so subtle that it's almost so obvious it's hard, I guess you could say. What do we want? What do we want our x coordinate to always be as a function of t? T, right? We want it to be t. We don't want it to change. We want the x to always be the thing we're plugging in, right? Because this x coordinate was always the thing we plugged in, x. So I'm going to call it t. What do we want the y coordinate to be? Whatever I plugged in squared, right? Which in this case would be t squared. So if I let the x coordinate be t, I let the y coordinate be t squared, I should draw the exact same thing. And you can check it again. You could do a t table. T, x, y. So plug in 0, you get 0, 0 squared. Plug in 1, you get 1, 1 squared. Plug in 2, you get 2, 2 squared. All we've done, though, is we put the domain in the background like a clock that's running. That's what we've done. We've taken it off our picture, and we still draw the same exact graph. -1 goes in, you get -1, -1 squared, which would be -1, 1. So you can do it yourself. You know, I expect that you could do that, and it would draw the same exact picture. Understand? Okay, if you have your graphing calculators, I'd like for you to take those out. Or any calculator. Now, if you don't have a graphing, I'm not sure how this is going to work for you. All right, we'll see. Most of you have graphing calculators? Do you have one? Do you own one? You do want. You have one, though. Do you have one? No? No, that's right. I forgot. Okay. You got one? You have one at home. Okay. So look, you should be able to get into what's called the mode function of the calculator. So go to mode. And somewhere in there, it gives you the option for graphing. And it should be selected on function right now. Do y'all see that? See if you can get into the graph menu and bring up options. And do you see one there that says parametric? Select parametric. And then go like you would normally go to graph something. So bring up where you put in the function. And what you should see instead now, what you normally see, is something like xt1 equals then yt1 equals. Do y'all see that? And then below that, it's what? xt2 equals yt2 equals. Yes? Okay, what these are these are groups of input Okay, xt1, yt1 is asking you to give the parametric equations for the first graph. That's why it's 1. If you want to graph a second graph, you could do 2, and then the third, if you want to do a third graph. So it's asking for the x and the y. And it's important that these are given as functions of t. So let's do the circle one first. And let's just use a radius of 2 to make this easy. I want you to type in on xt1, I want you to type 2 cosine, and then you have to use the t. But I believe if you hit the variable button, the variable button should have, like, it should say on there, xt theta, something like that. Just hit that and it should input a t. Do y'all see it? Did it work? Okay. Then go to the next one, 2 sine t. And then go ahead and at this point graph it and see what it draws. Did it draw a circle? Anyone not draw a circle? You got a circle? No circle. Okay, you might be in degree mode. If you're in degree mode, yep, put it in radian mode. And that's because, remember, when we're doing the trig functions, we're going to use radians instead of degrees. Yep. That's one thing on these calculators, if you ever get into trouble, always make sure you're in radian mode. You get it? Yep. So it doesn't look like a circle, does it? Like yours, it looks kind of like an egg. Did you get yours? It died. Did that one go? Yeah, so now let's talk about the zoom features. If you go to zoom, I think there's what, standard, square. If you go to zoom and select square, it should look more like a circle. And all that does is adjust your window. Y'all see that? Y'all with me or not? Yes? Okay, now what I'd like for you to do is I'd like for you to only draw half the circle. So if you're going to draw half the circle, don't you have to restrict t? Yes? You have to restrict t. So back in, this again goes back to how much comfort you have with your calculator. To adjust the variables, x and y in a traditional function, you would use this button called window, and you adjust your x and y. Here, try and get to the window option, and you should have a control on t in there, a t min and a t max. Do you see 10? Go back to your graph. Oh, uh-oh. Okay, mode. Pair, it's right there next, pair. And then graph, and then put them in. Do you find your window? Okay, so what is it? I think by default, it was 0. Okay, so you're in degree mode. That's fine. That'll work for you. Change it to 180. No, you're in degree. It's okay if you're going to stick with degree, but you're going to use 180 instead. And are you? It's in radian. Okay, then instead on your window, do pi, 0, and then just use your pi key. There you go. And now graph again. Should just draw the top half. Where is it? It was there, right? Yeah. Did you change something? Let's go back to window for a second. T-step, that T-step is way too big. Do 0.1. Yeah. There you go. T-step is like you know how we make a T-table? We're doing like, you know, you go 0, then you go pi over 4. The T-step is how big those steps are. And if you have 7 in there, that's a huge step, and it's not getting anything. That makes sense? Did you get it? Yeah? Yeah? Whoa. What the hell? Go bring up the functions. Radian mode. And then go to window again. Oh, it's your T-step. Okay, T-step needs to be small. 0.1, and now graph. There you go. What was happening was it was picking big chunks, and it was testing, and it made it look scattered. Yeah. Okay, y'all got that? Understand? So really, theoretically, everything that you've ever done with a function on that calculator, you could have done with this. So now I'd like for you to graph the parabola. See if you can graph this parabola. So you're just going to go in there and change t, right? Your x1, your xt1, and your xt2, change it to t and t squared. And then just hit graph, and it's only going to draw the right side. Because our restriction on t went from 0 to what? Pi, or 180? Now you want your t to go negative, so go back and adjust your window, and you should be able to graph the other side of the parabola. Yes? Yeah. Okay. Does this make sense? Graphing, the parametric function on the graphing calculator is very powerful, all right? Okay, I want to try a different one. Y'all ready? I just want you to graph this one. Use your calculator, right? Now, you could do a t-table also, right? I'm going to do a t-table while you're doing that just to show you how it could be done. So you could do it if you didn't have a calculator, doing it with the t-table, but the problem is you then have to try and connect the dots and figure out what it looks like. So it looks like your x-coordinate is a quadratic and your y-coordinate is linear, which is very much like this, right? Except reverse. Your x-coordinate here was linear and your y-coordinate was quadratic. This looks like a parabola opening up. What do you think happens if you switch it and now your y-coordinate's linear and your x-coordinate's quadratic? Parabola sideways. And so that's exactly what it would look like. And yeah, it's slightly moved, so it looks something like this. But this time, again, the big point here is that we can draw things now and not have to worry about vertical line test anymore, because it does not, we're not trying to act like this is a function of x. We're saying that the x and y coordinates are both functions of t. So that's called a parametric curve, all right? These are all called parametric curves. So if you have a parametric curve given by x equals some function of t and y equals some function of t on some closed interval, a less than or equal to t less than or equal to b. So in other words, you're restricting the domain, right, to a closed interval. Then x of a, y of a, that right there is the initial point of the curve. And x of b, y of b is the terminal point of the curve. It's the two endpoints, right? And then you have everything in between that connects those two dots together. Let's do one more example. This is an example just to use your graphing utility. Sketch x of t, or x equals t cosine t, y equals t sine t. And before you graph it, let's think about what it might look like. Let's do it on just the interval 0 to pi. What do you think this is going to look like? We just did this, right, a second ago, but it was 2 and it was 2, right? What if the 2 is always the radius, wasn't it, of the circle? So what if I let that radius be now a variable, t? Then as t gets bigger, what happens? Your radius gets bigger, right? But you start out at 0. So it's going to start to try and draw a circle, and as you move and it draws a circle, the radius gets bigger and bigger as you draw. So what does it look like? A spiral, doesn't it? And you can confirm it with your calculator. And if you draw more, if you go out further, maybe to 4 pi or 6 pi, then it's going to draw more spirals, but it's going to keep widening out as you go. Does it make sense that that would be the case? So this t right here controls the radius. Now, in my Mathematica program that I've been kind of using throughout the semester to show you things, there's a built-in function in this program called parametric plot. And what it does is it says, give me the function of x, give me the function of y. Then give me the restriction on this. They use u instead of t, or as their parameter. So if I wanted to do, I'm going to say t cosine t, t sine t, and I want t to go from 0 to, let's say, 4 pi, then I should get this. Yes? And what's really cool about this program is I can say, all right, let me control this. I'm going to call this m. Then I can use this function called manipulate. And I can control my m here. And I'll make it from 0.1 to 200 pi. There we go. So as I control, oh, that's a little too much. One more thing. plot range. I'm going to fix my window to be, let's say, 20. It's too much. There we go. There we go. That's what I was wanting. Something like that. See. So now we have something that maybe in real life we're dealing with something that's behaving like this, right? And we're starting to be able to get to things that model real life stuff better than if we always have to follow the vertical line test. If we don't pass vertical line tests, we can't do it, right? That's where we are right now. But now we're saying, okay, look, there are ways to still do this, still maintain the definition of what a function is, and it's going to lead us to some nice pictures, right? I think. Now look, I'll change this to t squared. It's going to look like a spiral again, nice and uniform the way it was. See, what's happening is that the x-coordinate, the radius in the x direction, is growing more rapidly than the radius in the y direction. So now it doesn't look like a circle anymore, does it? Understand? How about this? Change this back to t. How about if I do, instead of cosine t, what if I do cosine squared? Wouldn't that mean that my x-coordinate, this cosine would never become negative, right? Never become negative. As long as my t is going to stay between 0 and m. So let's see what this looks like. Right? And you can imagine you can go crazy with this. I mean, you can just sit here on a computer and have fun, draw all kinds of weird looking things, right? The idea, though, is that I should be able to go to any point on this curve and find the slope of the tangent line. I should be able to, because I don't have to worry about the multiple x value, or the x value going to multiple y values. That's not even in my mind anymore. All right. Let me see. I've got one more little thing to show you if I can find it. This is a cool one. If you take a wheel, right, and imagine you have, like, your car, and you have a nail in your tire, okay? There's a nail in your tire on your wheel on your tire on your car, right? What is the path of that nail through space? So as the wheel turns, what does the nail do? What's its path? And that's called a cycloid, right? So I want you to watch as the wheel turns, watch the path of that point. Okay? Like that. See it? So that is a pretty intense path for that, right? You know how when you're driving down the road and then all of a sudden you'll throw a rock out your tread of your wheel. You know what I'm talking about? You go drive off the dirt road and then you get back on the road and you get up to speed and then you start throwing rocks out the back. I mean, look at the path of these things. I mean, it's a pretty violent path. I mean, look at this right here. Look at that change. You have a massive change in direction there, don't you? I mean, you're going from down to an immediate back up, right? Where everywhere else on the path, it's just traveling through this arc, that red arc. So it's changing, but it's a gradual change until you get to that point. Then it gets thrown, right? So that path right there is called a cycloid, and the equation for it, you can find it on, I'll just write it down. It's up here. It's harder to see, though. Let me zoom in on that. I think it'll be easier to. This is it right here. okay? It's r times t minus sine t, that's the x of t, and then the y of t is r times 1 minus cosine t, where r is the what? Radius of the tire. And then t, of course, is just, it's like time, but it's a measurement of the angle of the rotation, okay? Now, I'm not going to derive that. The book actually shows a nice little derivation of that formula using some triangle properties, but I'm not going to. I just wanted you to see it's there. This is one of those nice applications of parametric equations, because a cycloid, is something that real life for sure you deal with, right? Things rotating, moving through space. What's the path of, point on that circle? All right, now the calculus of this. All right, now we want to see what we can do in terms of calculus. So we're moving on to the next section. Calculus with parametric curves. So up to this point, what I would expect you could do on a test is I give you a parametric equation, and you need to be able to graph it. Okay, so you're going to probably want a graphing utility to do that. And if not, you'll have to do it by hand, and that'll be slow and tedious. All right? And if you need a calculator, I think I have an extra one. You just have to get with me. All right? If you need one. Oh, who left? Was it this class someone left a calculator here? This one? Was it this class or my other class? No? No, I think it was someone over here, so no? Okay. Okay, so the calculus with this. We can, because it's our last day, we're not going to get into a lot of deriving where it comes from because time. I want to get to polar coordinates. So we know that when you have a regular curve, right, back in Cal 1, when you pick a point X, there's a corresponding Y value up here. And the slope of the tangent line here, right, that slope, M, the slope of that line was what we call dy dx. It was the infinitesimal rate of change in y with respect to x, dy dx, or y prime, right? That's what we called it. Well, turns out that if you have a parametric curve, right? So this time I'm going to draw my curve. And now you have a parametric curve. That if you go out to a point, there will be some x value, right? And some y value that goes with that point. Do you agree the red one I just picked? My picture's terrible as far as straightness there. Now, that x and y value will be determined by what, though? T, right? T is what gets you there. So the fact that there's another point right here and another point right here, that doesn't matter to us anymore because that point is uniquely defined with some t. But we should still be able to find the slope of the tangent line, right? At that point. And the slope of that tangent line, M, is still dy dt, dx, sorry. But since our parametric equations rely on t, all we're going to do is rewrite it this way. And do you agree that this is the same thing? So what I did is I'm saying I want to know what dy dx is. I still want to know the slope of that line, but because our functions are functions of t, I rewrote the top as dy dt and the bottom dx dt, and if you reciprocate that, right, divide and flip, that is dy dt. But this right here, dy dt, doesn't that mean the derivative of the y with respect to t? And this one means the derivative of x with respect to t. And those are just two derivatives we can take, the derivative of each of the parametric equations. So this is really a good thing. So let's do an example. That's the big deal right there. That's what the slope of tangent line will be. So as an example, find where the tangent to x equals 2 cosine t, y equals 2 sine t is A, horizontal, B, 1, and C, vertical. Now you could probably answer all these questions without doing any of the calculus just by looking at the picture, but I want you to actually see how this works using the calculus. All right, so we already know what that draws, right? It draws our circle, center at the origin, radius of 2. So I know that this draws this. I want to know where the tangent line is horizontal. So let's start with that. What does that mean? Horizontal means that the slope is 0, right? M, the slope of the tangent line is 0, but that means that dy dx is 0. Right? That's what we mean by horizontal. So we need to find dy dx. So dy dx, we just said was dy dt divided by dx dt. What was dy dt? So what's the derivative of y with respect to t? We go back up. Here's y, right? Take the derivative on both sides with respect to t. You get dy dt equals what? 2 cosine t, right? So we have 2 cosine t over, what is the derivative of x with respect to t? Negative 2 sine t, which is really just negative, I'll leave it as a fraction, cosine t over sine t. We realize that that's actually cotangent, right? But I'm going to leave it like that because I want to know when that's 0, don't I? When is this 0? So back up to this, I want to know when negative cosine t over sine t is 0. The only time that a fraction can ever be 0 is if the top is 0. So this turns into, when is cosine t is 0? I can ignore the negative, right? Because negative, I can just multiply both sides by negative 1 and it's gone. So when is cosine of t 0? So cosine, where is it? Pi over 2, anywhere else? 3 pi over 2, anywhere else? Aren't there infinitely many places where cosine is 0? So you would actually need to get all the solutions. So this is where your background in pre-cal comes in. You know, depending on how you look at cosine. I always look at cosine off the unit circle. Cosine is always the x-coordinate, right? Those are the two places where cosine is 0. But we need to represent those angles, I mean, because there's an infinite number of them. I can go around and keep coming. So the way I would do it is I say, okay, the measurement of this angle here is pi over 2. And then what I need to do is jump around to this one. So how much do I add to get to here? Pi. But then to get back here, I add another pi, and then back here another pi, and pi, and pi, and pi. So if I start at pi over 2 and just add multiples of pi, right? K multiples of pi, like, 0k or 1k or 2k or 3k or negative 1k. You get all the possible answers. That's one way to do it. The other way to do it, which I don't like, is just to know what the cosine function looks like, and then know where all these happen, and then come up with the same formula. It's your call. Are there any questions, though? I would hope you can get this. T is pi over 2 plus pi k or k pi. And it's understood here that k is an integer. So k is 0, 1 or negative 1, 2 or negative 2, 3 or negative 3. Some books use n instead, and it's understood that way. So those are the infinitely many places where this thing has a horizontal tangent line. And we can check it, right? I mean, if we go back up here, and if we were to plug in pi over 2, we would actually be at the top of this circle, and the slope of the tangent line up there would be 0. And if we go to the 3 pi over 2, we'd be down here, and the slope of the tangent line there is 0 also. So it confirms. All right, where is the slope of the tangent line? 1. So that's part B. Do I have to take the derivative again? No, I don't. I just need to use the same derivative, which was negative cosine t over sine t. I want to know when that's 1, right? When is that 1? So when you could multiply both sides by sine t, when is negative cosine t equal to sine t? And I, again, I would use the unit circle here. And I would say to myself, where on the unit circle are the x and y coordinates the same but off by a sign, right? So where are the x and y coordinates the same but they differ by a sign? And that would happen, what, here, right? This angle is negative root 2 over 2, root 2 over 2. So they're the same exact value, they're just off by a sign. And then over here in the fourth quadrant, same thing, root 2 over 2, negative root 2 over 2. Same values, opposite in sign. So how could we pick out all these angles? Let's see, what's here to here? What is it? 3 pi what? 3/4 pi. Okay, so 3/4 pi. 3 pi over 4. And then could I jump to this next one? How much would I have to add to jump? Pi, and then to get back there? Pi, so it looks like I can do the exact same thing. So 3 pi over 4 plus pi k, or plus k pi. And if we look at it again, go back to the circle we had drawn earlier. If you go to this point, what's the slope of the tangent line here? Looks like it's 1, doesn't it? And then the slope of the tangent line here would also look like it has a slope of 1. With me? Part C. Where is the slope vertical? What does that mean? What's the slope of a vertical line? Undefined. So where is the slope undefined? That means where is negative cosine t over sine t undefined? When does that happen? When what is what? When sine of t is 0. Right? If sine of t is 0, this thing's undefined. So where is sine 0? And then you go through and you play the same game. Sine is 0 at 0 and pi. Right? The two ends, 0 and pi. So you would say that t is equal to 0 plus k pi, or you could just say k pi. Verification of that visually is that here at these points, our tangent lines are vertical at 0 and pi, or 2 pi, or 3 pi, or 4 pi, or 5 pi, or 6 pi. All right? So if someone gives you a parametric curve, they could ask you, you know, what's the slope of tangent line? What's dy dx, which is just derivative. And then they could say, when is it equal to this? When is it equal to that? When is it horizontal, vertical, or equal to a number? All of them require you having to investigate this a little bit. Yes? All right. Let's try this one. For the cycloid, x equals r theta minus sine theta, y equals r times 1 minus cosine theta. Whoa. When is tangent horizontal and then how about vertical? Now I want you to notice something here. I'm using a different variable, aren't I? I'm using theta instead of t. And that just means that these two right here are x of theta, y of theta. So I'm just using a different parameter. The parameter now I'm using is theta. So do you agree that for both of these questions about the tangent line, we need the derivative, right? We need dy dx. And dy dx is going to be dy d theta over dx d theta. So I'm using theta instead of t in that formula. So what is the derivative of y with respect to theta? So r is a constant, so just leave it here for now. What's the derivative of the inside here? What's the derivative of this? Just sine theta, and then you have an r in front of it. So r sine theta over, now be real careful here, what's the derivative of the inside of this? 1 minus cosine theta, because derivative of theta is 1. Over here it was a constant, derivative of constant was 0. So derivative of theta is 1, derivative of sine is cosine, and then you have an r in front of all that. Yes? R's cancel? Sine theta over 1 minus cosine theta. There's your derivative. Now, answering when it's horizontal. What does that really mean? The slope must be 0, which means that our derivative has to be 0, but the only way that fraction can be 0 is if the top is 0, right? So this is going to happen when sine theta equals 0, and we already showed that that happened when theta is k pi. How about when it's vertical? Slope is undefined, right? which means that 1 minus cosine theta must be 0, which means cosine of theta must be 1. And when is cosine of theta 1? Every 2 pi, right? Every 2 pi. So at 0, it's 1. At 2 pi, it's 1. At 4 pi, it's 1. At 6 pi, so all even multiples. So I'd write it like this. Theta must be, how about 2 pi k? That would give me all the even multiples of pi. Questions at all? You would have a pretty weird looking curve. Where's that? At what value? It would have to be the same theta for both. Oh, yes. Okay, so what happens? What is happening at, which one would it be? At 2 pi? You're getting an indeterminate form, right? So you would have to do some sort of limit. If you wanted to know what the tangent line was going to, the only thing that we know is that it's undefined there. And from the picture is why we know the tangent line was vertical. See, that's right here. You see that? Our tangent line is almost like the radius line, isn't it, of that circle? And you see that tangent line is trying to become vertical, but it's a negative slope as you come in from this side. As soon as you get past that point, the slope of the tangent line on the other side is positive. So if you really wanted to know without this picture, you would know where it's undefined, but then to check that it's vertical, you'd have to do a limit from both sides. So it would just be a limit problem. Take the limit of this as theta goes to, let's say, 2 pi or 0, and then L'Hopital's rule, and you'd have to do a left and right limit to check signs. All right. How about, that's tangent lines, right? That's derivatives. How about areas? The area between a parametric curve x equals x of t, y equals y of t, and the x-axis is, all right, so let me draw a picture first, all right? If we have something like this, we want this area. See, the difference between this and what we had before is that that blue curve is not y equals f of x. That blue curve is this parametric. So what we need are two endpoints. Just like for integration, we needed two endpoints. So this thing needs to be defined right here, where t is between, let's say, a and b. then we'll have the area is equal to the integral from A to B of y of t times x prime of t dt. Again, without getting into it, the book kind of goes into it a little bit, but we're just looking for a formula so we can see that it can be done. All right, so let's see what this is saying. You're going to integrate with respect to t, which is our independent variable. You're going to go from the beginning to the end, right? And then you're going to take the y component, or the y function of y, and then times the derivative of the function of t. And it just turns out that this right here is really like your dx before. And this is like y of t is like the height of the function. So we can use this as an example. Couldn't we find the area of a circle? Could we find the area of a circle? Let's try it. Find area of circle, radius r, centered at origin, using parametric equations. So what we'll do is we're just going to draw the top half, right? Draw the top half, and then what we'll do is find the area under that and we'll double it. Agreed? So tell me about the parametric equations for this circle, this top half. X will be what? R cosine t. Y will be r sine t. And tell me my restriction on t. 0 to pi. That will draw the top half of the circle. I had you do that on your calculator a little while ago, right? So that the true area, right, the area of the entire circle will be double the area under that, right? So the area that we want will be twice the integral from where to where? 0 to pi of what? R sine t, that's your y of t. I'm just spitting off the formula now, right? This is our y of t. And then times the derivative of the x, which in this case would be what? Negative r sine t, and then dt. Go with me? I can pull out a negative r squared, can't I? So this becomes negative 2r squared integral 0 to pi of sine, what, squared t dt? How do we integrate sine squared t dt? What do we use? Half angle identity. So I'm going to turn this into negative 2r squared integral 0 to pi, and that turns into 1/2 minus 1/2 cosine what? 2t dt. And now integrate these term by term. So what's the antiderivative of 1/2? You get, what is it, 1/2 t? And then what's the antiderivative of all this right here? It's been a long time or something, right? Antiderivative cosine 2t? Okay, include this part. It'll be negative 1/4 sine 2t. And then evaluate that 0 to pi. Let's try and plug in here. Plug in pi. We get pi over 2 here. Plug in pi. What's sine of 2 pi? 0. 0. So you get pi over 2 when you plug in pi. So you got negative 2r squared. You plug in pi, you get pi over 2. Then minus, now plug in 0, and you get what? Plug in 0, get 0, right? Which turns out to be, at the end, what? Negative pi r squared. Now, it gave us a negative area. Why do you figure that is? I mean, it's correct. It's just off by a sign, isn't it? Why do you think that is? Let's look at the formula here, right? Do you remember that do you remember in a traditional integral, the width of our rectangle was always dx, wasn't it? That width? And it was the change, and we always moved from left to right, didn't we? We were moving from left to right. When we draw our circle with this parametric curve, doesn't it start at the right and go to the left? So our change in x is actually a negative change. And so we're getting the correct area, but there's a negative change in x, so we're off by a sign. So we could easily resolve that issue by just looking at as the absolute value of this. We just have to keep in mind that that could happen. We could get a negative value. It just depends on the direction in which the curve is traversed. The point, though, overall, is that you can find areas under parametric curves still. So you can take derivatives like you did in Cal 1, find slopes of tangent lines. You can do areas like you did in Cal 2, right? But now with parametric curves. Next thing, arc length. Now, we're not going to get crazy and be like, okay, take this parametric curve and rotate it about this axis. We're not doing anything like that. That would get way too complicated. But we just want to see that a lot of what we've done extends out. So do you remember the formula for arc length back when it was a function of x? It was something like length equals, like, what was it? Integral square root 1 plus, was it like y prime squared dx or something like that? Okay. And if you go back and you look at it, I derived it for you. I did it once in class, and I came back, I think, the next time or later that day, and I said, you know what, I want to clear that up because I didn't like the way I derived it the first time, and I did it again. If you go back and look at that, you'll see that this right here, this 1 came from doing dx dx and saying dx dx was 1. Well, this time, dx dx can't be dx dx because our variable is t. So this dx dx is actually a dx dt and then squared. And this one right here is not dy dx, it's actually dy dt squared. So all that changes in the formula for arc length is this. Integral, now we'll have a to b, square root, it'll be, how do I want to do it? I'll say dx dt squared plus dy dt squared dt. And this is, again, making sure you understand if x equals x of t, y equals y of t. So we are dealing with the parametric curve, and we are on some interval of time like this. Important thing about this formula, okay, is that the only way, there are some problems you could run into. Watch. When you draw this curve, it's getting you the length of this curve, right? And it really doesn't matter what this curve does, as long as this curve, we'll call it C, C can only be traversed once for this formula to apply. Think about the first example I gave you. We drew a circle, didn't we? We went and we drew a circle. But we said if we went to 2 pi, we'd start drawing the circle over itself, wouldn't we? So if we went from 0 to 2 pi, we would have drawn one circle, right? If we would go 0 to 4 pi, what would happen? We would have drawn a circle on top of a circle. This formula will not work if you're drawing a curve on top of itself. So that only applies if that curve C that you're trying to find the length of is traversed exactly once. If it is, we're good to go. So how bad do we want this to be? As an example, find the circumference of circle radius r. So we've used the area formula to verify the area of a circle, right? We're going to use the arc length formula to verify the circumference of a circle. And let's use the parametric equations for the circle. So how can I set up this length? Length will be what? Integral. Now where am I going to go from? 0 to 2 pi, right? Does it matter that 2 pi and 0 overlap? Like at 0 you get a point, right? When you come all the way around to 2 pi you get a point again, right? It's actually okay because the length at a single point is 0. So right, if I say how wide is the point 1, it has no width. So that's okay. You have to have an interval to have length. All right, so square root of. Now, I'm hoping that you're keeping track over there in your mind that we're using these, right? Parametric curves, equations. Sorry, I wrote that down wrong. X is r cosine t, y is r sine t. So we're going to take the derivative of this one, which is, what's the derivative of this? Negative r sine t. And we are going to square it. Then we're going to say plus, we're going to take the derivative of the other one, which is r cosine t, and we're going to square it. And we're going to do that whole thing with respect to t. And this is really, really nice, right? What happens here? This is r squared sine squared t plus cosine squared t. Right, you square both of these, the negative goes away, so you get r squared sine squared t, r squared cosine squared t. You factor in r squared out of both of them, and sine squared t plus cosine squared t is 1, isn't it? So this turns out to be the square root of r squared, which is just r. Man, that's nice. It's the antiderivative of r with respect to t, rt, and then 0 to 2 pi. Plug in 2 pi, 2 pi r. Plug in 0, 0, 2 pi r. Isn't that the circumference of a circle? Curious, what day was it that we did arc length? That's factorial. Let me see, day 5. No, day 6. Maybe day 7. Volume. I think we're getting close. Surface area. Here we go. This was it. Find the length of this. Find the length of that. I didn't show you the area of, we didn't do circumference of a circle? Damn it. We didn't do it using the old formula. And I was trying to illustrate, I was going to try and contrast the two different approaches to make you appreciate this a little bit. I'll show you, I won't do the whole thing, but I'll just show you the setup. If you were to try and find the circumference of a circle using the old way, you would first have to come up with a way of defining this first part of the circle, which you would use y is equal to the square root of r squared minus x squared. So you'd have to find the general equation of a circle, radius r. You'd have to solve it for y, which would be this. And then you would have to take y prime, which would be negative 2x over the square root, 2 again, r squared minus x squared. That would be your derivative. You'd have to square it. Then you have to plug it into that thing, 1 plus that derivative squared, square root, clean the thing up, and hope for the best. And I think it turns out to be extremely ugly if you do it. Do you understand what I'm saying you would have to do here? It's kind of a mess. And you can see with the parametric, I mean, this Pythagorean identity saved our ass, didn't it? Really did. Okay. All right, that's it for That's it for 9.2, which is parametric curves. So let me give you a little bit of stuff to look at from there. Page 513. And I realize our test is like 48 hours away, so I'm not going to overload you with this thing. Maybe something like 13, 15. $29 is an area problem. 37 is an arc length problem. 39 is an arc length problem. So 13 and 15 is like find where the tangent is horizontal or vertical. 29 and 37, 29 is find the area, 37 is the length of the curve, 39 is length of the curve. Okay, that's a reasonable amount of problems to do between now and next time we meet. Take a break. Take a little 10-minute break, and then we'll come back and we'll look at polar coordinates. All right, so we're going to move on to a new section, and the last topic we'll cover, polar coordinates. Now, I mean, just kind of to stress to you, what we covered, parametric equations, we could spend like, good 2 solid weeks on that and get really deep into it. But usually at the end of a Cal 2 class, we just kind of brush over this, because if you were to take more math classes, you'd be exposed to it again. And so a lot of times when we're exposing students to this stuff in Cal 2, or Cal 3 or higher, we kind of assume you haven't seen it, or it's been a while, you forgot. So we kind of readdress it fully when you see it again. So polar coordinates. Now this is very different than parametric equations, even though it's going to look somewhat similar. It's kind of a different concept. What we're doing is we're actually changing our coordinate system. All right, so what we're familiar with right now is what's called Cartesian coordinates. And the Cartesian coordinates are based upon the fact that we have a 2-dimensional plane, right, 2D, and that to get to a point in the 2-dimensional plane, we just have to supply you with 2 pieces of information. We have to give you a distance to go along the x-axis, and then a distance to go vertically parallel to the y-axis, which would be your y-coordinate. And if you follow those instructions of going out x and up y, you will find yourself at the point xy, right? That's Cartesian. So everything is done in almost like a grid format. And a lot of times when you see like graphing paper, right, everything will be done like, real light lines like this, and then your traditional graph paper looks like this, because everything is left, right, up, down, right? That's how you move around. So that's our Cartesian coordinate system. Polar coordinates work in a different way. Polar says, look, we're going to have to, let's try and get to that same point. In Cartesian, I needed to give you 2 pieces of information to get to that point, right? An x and a y. But in polar coordinates, we're going to get to the same place, still giving you 2 pieces of information, but those 2 pieces of information have nothing to do with how far to go out x and up y. Instead, I'm going to tell you how far to walk out, and I'm going to tell you an angle to turn. And if I give you those pieces of information, you should also be able to get to that point with just those 2 pieces of information. So we call this, instead of our x-axis, we call this our polar axis. All right? And the polar axis is always where we would start. Imagine you're standing at the origin, okay? And we're looking, it's almost like we're looking from the top down on this. It's like a person standing here. And you always start by looking out the polar axis. And now I'm going to give you 2 pieces of information. I'm going to tell you how far to walk out, but I'm also going to tell you how much you should turn before you walk out. So you could do it the other way. I tell you how far to turn, and then I tell you how far to walk. The amount that you turn is your angle, which is theta, and the amount to walk out is r, which is almost like a radius. So this point right here, instead of xy, I'm going to call it r theta, where theta is the angle between the polar axis and the line segment connecting the origin to the point. That's your angle. And then the radius, of course, is the distance from the origin out to the point. So if I give you those 2 pieces of information, you should be able to get to that same point, right? Questions? These are called your polar coordinates. The center of the graph, which we call the origin in previous classes in Cartesian, we call the pole. And so let's just practice graphing a few polar points. All right, let's just see what they look like. So as an example, plot the polar points. Let's do a couple of them. A. How about 1 pi? How about B? 3 pi over 2. Sorry, wrong. 4 3 pi over 2. And the last one, how about -2 pi over 3? Let's try and do them all on the same grid, or on the same polar plane. So what is point A? I'm gonna turn by pi, right? I'm gonna rotate by pi. So I'm gonna rotate by pi. That puts me like this. There's pi. And I'm gonna walk out how far? 1 unit. So let's just say 1 unit is right here. Right? That's the point. It lies on the x-axis, doesn't it? How about the next one? 3 pi over 2. I'll call this A. 3 pi over 2. I rotate through 3 pi over 2. Oh, let me see what this is real quick. Oh, that is it. Okay, so you rotate it here by 3 pi over 2, and you walk out 4 units, which would put you somewhere way down here probably, right? Now, the next one is somewhat interesting because you would think that r being your radius would imply that you need to always be positive. But with polar coordinates, it's okay to have a negative radius. It just means instead of walking forward, you're going to walk backwards. So you rotate by pi over 3, which would be somewhere, I don't know, what do you think? Somewhere around in here, right? This would be your angle, pi over 3. But instead of walking out into that first quadrant, you're actually going to walk backwards and go out 2. So that would put you out, somewhere around here. That would be C. B would be here. Okay? Make sense? We good? Okay, now let's look at something more interesting, all right? And that is, what is the connection between Cartesian and polar? I mean, there's obviously some way to connect the two together, right? So connecting, or connections between polar and Cartesian. And we'll start this by just going with a general point sitting out here. We know that in Cartesian, we have y here, we have x here. But in polar, we have the angle and we have the radius, right? So geometrically, you can tell what the connection is between these things. We have a couple of them. First of all, how about Pythagorean identity? What does the Pythagorean identity give us? X squared plus y squared should be equal to r squared, right? So that is one of our main connections. If we know the x and the y, then we actually know what the radius is, right? We have the relationships we had earlier when we were doing the circle with parametric. We have a way of determining x in terms of r and theta. So just, write out cosine theta is x over r and then solve for x. And same thing here. So these are two more connections that we have. So the first one was, if we know x and y, we can get r. This next one says, if we know r and theta, we can get x. And we can also get y, right? And the last thing is, can we ever get theta if we know x and y? Can we ever determine this angle if we know what the x and the y coordinates are? Well, the relationship between theta and y and x is tangent of theta is y over x, isn't it? And I'm not going to write that down there because that's not the formula I'm in a box. We know tangent theta is y over x. So what would theta be? Take the arctan or tan inverse on both sides. So we get this final relationship, I'm almost out of room, that theta is arctangent of y over x. And we have to be a little careful with this one. I'll put a little star next to it, because we know that there are some domain restrictions on arctangents, right? So when we go back and try and recover an angle, sometimes we'll have difficulty because we need to actually determine what quadrant we're in, all right? Okay, so those are your conversion equations. That's how you could get from polar to a Cartesian or back from Cartesian to polar. So let's do an example of a conversion. Convert from polar to Cartesian. And here's the point. Let's do 4 2 pi over 3. This is fairly simple, right? We have r, we have theta. What we need is to convert this to x and y. So if you know r and theta, what's x? R cosine theta, so 4 cosine 2 pi over 3. And y would be 4 sine 2 pi over 3. So x would be 4. What is cosine of 2 pi over 3? So cosine of 2 pi over 3? You can use your unit circle. Just don't get your calculator out, because that'll be the worst thing you could do. Look, pi over 3 is here. 2 pi over 3 is here. What's the x coordinate of that point? It's one of the common ones. No? Negative 1/2? What's sine of 2 pi over 3? Root 3 over 2? Could you get that if you had a unit circle? Yes? Okay. So x is negative 2, and y is 2 root 3. And so in Cartesian, it's the point negative 2, 2 root 3. That would be the answer. let's try the other way. Let's go from Cartesian to polar. Convert from Cartesian to polar. And how about we do the point -2, -2. So we're given in this problem x and y, right? We're trying to get it over to r and theta. So r, by definition, the connection between r and x and y is that r squared must be x squared plus y squared. So r squared must be, let's see, x squared would be 4, right? And y squared would be 4 again. And that means r squared is 8, which means r is the square root of 8, which is 2√2. So we know what r is. Now theta. So to get theta, we take arctangent of -2 over -2, which is the same as arctangent of 1. And if you were to use your calculator here, what angle would it spit out? Where's the ratio of the y and x coordinates 1? What do you get? If you're in radian mode, it might be hard to tell unless your calculator's smart. It's pi over 4. It's 45 degrees or pi over 4. We will use pi over 4 because what? Because in polar coordinates, we want to use radians, all right, for our angle, radians, not degrees. But this is incorrect. And I'm giving you this example because I want you to see this is where the limitation of the arctangent and the restriction on domain gets us into trouble. Where is this point? And plot it. -2, -2, right? We should be down here. This is saying that we should turn by pi over 4, which would put us in the first quadrant, and walk out 2√2. That's only because the arctangent doesn't look over here, right? The arctangent is defined between -pi over 2 and pi over 2. So it's always going to spit us out an answer in those first two, or in the first and the fourth quadrant. So we need to realize that. We need to realize that the pi over 4 that the computer is returning to us is actually just this reference angle, pi over 4. And so we need to add the pi to it in order to get ourselves into the right position. No, because -pi over 4 would put you down here, right? It would be a backwards rotation. I don't know if that's what you mean, but that. Oh, okay. Yes, you could leave this as a pi over 4 and you could change that negative. Yes, you could, because that would get you to that same place. But just be aware, that's all. I just want you to be aware of not just taking that angle right for what your calculator tells you. Always check to see what quadrant you're in to make sure that you've got the right angle. So I'm going to say our polar point is 2√2, and then the angle. What is pi plus pi over 4? Is it 5 pi over 4? There's your correct polar point. All right, now this is just the setup of what polar coordinates are, how they're connected to Cartesian coordinates. Now let's take a look at why it is that we like polar coordinates sometimes over Cartesian coordinates. Polar curves. The equation R equals f of theta is called a polar curve or polar equation. As an example, let's look at this. R equals 2. So, look, a polar curve or a polar equation is where your radius, which is how far you walk out, is somehow a function of the angle in which you're pointing. So remember, if I'm standing here and I'm looking out the polar axis, someone gives me the angle to rotate, and then how far I walk out is dependent on this angle. So every distance I walk out depends on the angle that I've rotated. That means the radius, the distance I walk out, is a function of the angle theta. Any curve that's drawn that way is called a polar curve. This is a very simple example of one. The radius I walk out is 2. Do you see the angle in here anywhere? Do you see theta? No? That means that if I'm pointing out the polar axis, I walk out 2. If I rotate by something, I still walk out 2. No matter what angle I plug in, I walk out 2, right? So the distance I walk out is actually, in this problem, in this example, independent of theta. So for all theta, it's always 2. What's it going to draw? Circle radius 2, right? Every single time I rotate, I start out, look out the polar axis, walk out 2. Rotate a little bit more, walk out 2. Rotate a little more, walk out 2. Do the whole thing, you're going to have a circle of radius 2. But isn't that a very simple equation compared to the Cartesian equation for this circle? What's the Cartesian equation for this circle? X squared plus y squared equals 4. And we know that working with that equation in Cartesian is a little bit troublesome sometimes, right? Compared to that equation, which is like a constant equation. So very, very easy to mess with. Here's another example. This time, I'm not going to write r as a function of theta. All I'm going to do is this. Theta is pi over 4. So now I'm telling you that to figure out your points, you have to fix theta to be pi over 4. And then your radius, there's no control on the radius here, right? It doesn't say what radius can be, so that means radius can be anything. So that means you're going to look at down the polar axis, you're going to rotate pi over 4, and you're allowed to walk out as far as you want and go backwards as far as you want. So what is this going to draw? A straight line. It's going to look like this. This is the equation theta equals pi over 4. This up here was the equation r equals 2. Understand? No questions? All right, next example. Now one that's a little more interesting. R equals 2 cosine theta. Let's try and figure out what this draws. Okay, let's try and figure out what this draws. And maybe we can do it with the t-table. Theta is what's controlling everything. The radius is determined by that. So let's start by pointing straight out the polar axis. What's theta? 0? Okay. 2 times cosine of 0 is 2. Now this gets a little weird when it comes to graphing, right? I mean, I talked about the graph paper for like Cartesian, looks like a grid. Well, if you go to, you know, Google polar graph, polar graph paper. This is what polar graph paper looks like. See if I can bring this up. Cartesian, polar graph paper, PDF. Let's just do that. Come on. Yeah, you can put all these different specs into it to make the graph paper change. But here's an example of polar graph paper. So look how this would work. You know what I'll do? Just grab that piece and come in here. So if I want to graph this, right, I'm going to go 0, 0, 2. That means I point out the polar axis, right, and I walk out 2, right? So how about 1, 2, right about there? Understand? From the pole, I walk out 2 as I'm pointing out angle of 0. Now let's do another one. One of the common angles. How about pi over 4? So this will be 2 cosine of pi over 4, which is 2. Cosine of pi over 4 is root 2 over 2, which is just root 2. Agreed? Root 2 is about 1.414, something like that. So on my paper, what I'm going to do is I'm going to rotate by pi over 4, which looks like, what? Where's pi over 4? This one right here, right? This line. So I'm going to be down, and I'm going to go out 1.414. I need to extend this polar line right here. They didn't give me this in here. You'll see that little line. I walk out 1.4, which would be somewhere about right there, and I draw a dot. Understand? And then I keep doing this, right? I keep doing this. How about at pi over 2? Where would I be? What's cosine of pi over 2? 0. So that means I rotate to pi over 2, which is straight up, and I don't walk out. I just stay at the pole. So that would put me here. And if I kept on going around, what you would get, and if you filled in all the other pieces, I'm not going to do it, is you would get this right here. It's actually a circle that's offset to the right a little bit. That's what it would look like if you went in and plugged in more points. Do you understand, though, how the polar graph paper would work, though? Just get your angle, walk out your distance. Angle, walk out distance. The more angles you use, the better off you'll be. Now, I already had one of these done. Let's see. There was a constant one. This was an example. This is an example of where you have a constant radius, right? So no matter what angle you point at, your radius is always fixed, right? This is the one that we just looked at. So as I change my angle, I go around. See, pi over 4, it was 1.4. This one actually comes out. You can really see it a lot better. Because if this is 1, right, and this is 2, then 1.4 looks like about right there. And if you would have used pi over 3, which we didn't, if we would have used pi over 3 and plugged it in, it looks like we would have been somewhere around 1, really close to 1. Then if we would have used 5 pi over 12, we would have been down here somewhere between 0 and 1. Then when we plugged pi over 2 in, we actually got 0, and then it went backwards and did the same thing. Got it? Now, believe it or not, your calculator can be switched into polar mode, right? So try it. Pull up your calculator, go to your mode function, and switch. You're in parametric still if you didn't switch back. You now go to polar, and when you go to polar, it's going to show you something like, it's been a while, let's see. Should give you like R1, R2, R3, right? So on your calculator, go to polar mode, and then on R1, go ahead and type in the one we just did, 2 cosine, and then they want to use the angle. The variable here is theta, and you should, your variable key they use for x should say xt theta, and you should be able to use that. And go ahead and plug it in and plot it and see what it gives you. Make sure you're in radian mode, I guess. Mine didn't draw it because I'm in degree mode, so I'm going to switch to radian. Was it 2 cosine theta? Oh, I never changed it. I was like, why is it drawing something completely different? 2 cosine theta. Looking for my theta. There it is. Yeah, mine drew it, and it's kind of small, so you'd zoom in. Also, hit the window function, and you can adjust your theta again. And it's by default, it's 0 to 2 pi. Just like we adjusted the t, you can adjust theta. Okay, so just wanting you to see you can do this on your calculator. Now, your calculator does not allow you to do that line that we did where it was theta equals pi over 3, where we fixed theta. You can't do that here. You can do r equals 2 and draw a circle. You just can't do a fixed theta. Now, looking at this polar equation that we just did, it looks like that's a circle, doesn't it? Yes? Can you get this to Cartesian? In other words, if it is a circle, then it should have a Cartesian representation, shouldn't it? Let's see if we can get this to Cartesian. So how could we do that? Well, we want the whole circle, the whole curve, not just one point, right? We know how to convert a point to Cartesian, but how do you convert an entire curve to Cartesian? So let's take a look at what we know. We know that r squared is 4 cosine squared theta, don't we? Yes? We know this. And we also know that r squared is x squared plus y squared, don't we? Okay. So, let me turn this off. So we could from this write that x squared plus y squared equals 4 cosine squared theta. Anything else we could do? Don't we have this? Don't we have x is equal to r cosine theta? Isn't that one of those boxed formulas I had? Doesn't that mean that x over r is equal to cosine theta? Doesn't that mean I can come up to this equation right here and I can replace the cosine theta with what? X over r, couldn't I? So I could say from this equation up here that r equals 2 times x over r. or r squared equals what? Two x. Now, how could that help me? How can that help me? I mean, you could look right at this, couldn't you? Look at that equation right there. See, if I'm trying to get to Cartesian, aren't I trying to get everything in terms of x and y? Everything. So what I did is initially I said, okay, I square both sides. I know that r squared is related to x and y. And I tried to rewrite it, but then this side over here had theta in it. So now I'm trying to get this cosine theta to somehow have an x in it. I use this relationship over here, but when I do this relationship, I realize that I actually could have replaced this r squared with what? 2x. And so this equation right here would just turn into 2x equals x squared plus y squared. Is that an equation in terms of x and y only? Yes? Is that a circle? Does that look like a circle? Not quite yet. What we would have to do is this. So follow through with this and see if you buy it or not. You agree with that? Just move the 2x to the other side. Now, on this piece right here, I'm going to complete the square. Now, why am I doing this? I know the reason why I'm doing it is because I know that all circles in Cartesian coordinates can be written this way. Do you all agree? This is a circle centered at HK, radius R. Are we familiar with this? I think we talked about this at least once. This is a circle centered at HK, radius R. I'm trying to make this look like this. So I moved everything to one side. I'm going to complete the square here. When I complete the square here, I take half of what's in front of x, so that's what, -1? I square it, 1, so I'm going to add and subtract 1. So this becomes x squared minus 2x. Add 1, subtract 1, still had y squared, equals 0. What do these first three guarantee to factor to be? X minus 1 squared. What about this -1? What am I going to do with this? How about we move it to the other side? And wouldn't that make it equals 1? And what's still over here? Plus y squared. Does this look like this? Yeah. It's actually a circle. Where's the center? What's HK for us here? 1, it's the opposite, be careful. 1, 0, right? Because in the formula it's x minus h, so if we have a minus, we use the opposite. So it'll be 1, 0. We're saying that this is a circle centered at 1, 0 with the radius of what? The square root of this side, radius of 1. Is that what we drew? Is that what we drew? Yeah. It was a circle. Remember, this was from here to here was 2, wasn't it? So we know that the center of it is 1, and it's a circle centered there at 1, 0, radius 1. This whole thing of going from polar to Cartesian, or Cartesian back to polar, is a little tricky, but I want you at least to be exposed to it so you've seen it before. If you ever see someone take a polar curve and all of a sudden say, oh, but obviously that's this circle centered at this point. This is what they're doing. They're manipulating things using the connections between polar and Cartesian to get it into Cartesian form. All right. Now for the next thing, let me bring up my, which one is this? Okay. I just want you to see some of these other ones. This is the polar curve 1 plus sine t. R equals 1 plus sine theta. All right, that's what we're about to look at. I'm not going to ask you to graph this by hand. but as the next example, r equals 1 plus sine theta. If we were to go through and graph this using your calculator or by hand, you would get this. So as you move around, comes back, almost looks kind of like a, what, I don't know. Just repeats itself though, can you see? Just keeps drawing itself on top. See, how about this one? 2 minus sine t. That's what 2 minus sine t looks like. Oh, cosine kt. This one's interesting. R equals cosine. Let's go cosine 2t, or 2 theta. You want to see what that looks like? Let me get my k. 2. Yeah, I'm starting with 2. That's cosine 2t, 2 theta. So as you draw this one, you start out there, looking out from the pole to down the polar axis, you draw that first point. And then when I complete one full, how should I say this? Because it's 2t, that means between 0 and pi, I should complete like 1 period. So let me bring this up so you can see what's happening here. Let me get to, here's 1 pi, which is right. Did I pass it? No. There's pi. Okay. So let me go backwards so you can see this. When it draws it, follow the path, okay? It draws up first, and then watch what it does. It comes down, right? And then it goes up, it goes through the pole, and then back across, you see? So a lot of times people think that it's drawing it like this, but that's not what's happening. It's going like this, around, back through, and then what? It's probably going to go like that, and then back through, and then start repeating itself. You see that? And play it through here. Goes up and around. And you could only really get this by taking a look at the table and seeing what's happening. See, when we are here, let's see, what angle are we at? Right. Bring it all the way back to the beginning. Okay. We are right here. Let's do it right there. Our angle is 11 pi over 36. Where is 11 pi over 36? Probably somewhere in here, right? We're aiming this way, but our radius is turning out to be what? Negative, so we come backwards. Kind of interesting. Now, what happens if I change it? Instead of 2 theta, I make it 3 theta inside. So I'm changing the actual function now. Then it draws this. What if I change it to 4 theta? Oh, well, that looks kind of familiar, right? More petals on that leaf. 5 theta, 6 theta, 7 theta, 8 theta, 9 theta, 10 theta, right? Start to get to some pretty interesting looking curves, right? All right, so what is it that we want to know? I mean, drawing this is not simple, okay? It's not this obvious thing. How about all we do is we look at the derivative, okay? We won't do areas. If you're interested in areas, there's some stuff in here. It's the next section, areas and polar curves. Let's just do the derivatives and we'll call it a semester, all right? So derivatives or tangents to polar curves. So given r is some function of theta, So you have a polar curve. Then dy dx is equal to dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta. That's a pretty complicated looking formula. Yes, it's not as nice as the last one, but they get it the exact same way. I'll show you the derivation of it right below it, but it's not something you really need to know. Dy dx is equal to, you could write dy, what, d theta over dx d theta. Right, do you agree that that's what dy dx is? But remember that x is equal to r cosine theta and y is equal to r sine theta, isn't it? Yes? But what's r? R is a function of theta, isn't it? So this right here, x, is some function of theta times cosine theta, and this y is some function of theta times sine theta. I'm replacing the r with this. Now, what's dy d theta? Look at this right here. What's the derivative of y with respect to theta? What would you have to use if you're taking derivative of this times this? Product rule, wouldn't you? Wouldn't you have to take the derivative of this product rule? So you would have to take the derivative of this, right, with respect, times this. That's this part right here. You're taking the derivative of r with respect to theta. Derivative of r with respect to theta is the same as saying the derivative of f with respect to theta. So f prime times sine is this piece here, plus product rule, this times the derivative of this. But what is this by itself? It's really r, and then cosine theta. So that's your product rule on top. And then when you do the second part, which is the dx d theta, it's the product rule on this one. Does that make sense where that comes from? Okay, so that's the formula. Let's see if we can actually do an example. This is what you need to know. So as an example, if we take this thing called a cardioid, which is 1 plus sine theta, I think we graphed that just a second ago, didn't we? I said, what does that look like? 1 plus sine, no, this one right here. There it is. They call it a cardioid. Kind of looks like a what? Like a heart, not like a real, oh, cute heart. I mean, it looks like a real heart, like, you know, from the top, it looks kind of like a heart. So, cardioid. So take that and let's find where tangent is horizontal and vertical. So same thing we did before with the parametric. We want to know where the derivative is 0 and where it's undefined, right? Those are the two things. So we need the derivative first. What's the derivative of y with respect to x? Okay, use the formula we just had. dr d theta times sine theta plus r cosine theta. What's dr d theta? Right here. Cosine theta? times, what was after dr d theta? Was sine theta. So times sine theta. And then plus, what was next in our formula? R cosine theta. And that doesn't change, right? R, well, what's R? 1 plus, let's replace the R. 1 plus sine theta. And then, what was it? Cosine theta? All over. So you're doing dr d theta, right? Which was the same thing we had before. Cosine theta. But then times what? Cosine theta again. Minus, right? Minus what? R, which is 1 plus sine theta times sine theta. There's our derivative. Understand? Let's put things together. This is just cosine theta times sine theta. Here I distribute a cosine through, cosine, and then here's another cosine theta, sine theta, right? So I'm going to have on top a cosine theta plus 2 cosine theta, sine theta over, what do we get here? Cosine theta squared minus sine squared theta if you want, and then minus sine theta. That okay with you? Would you like to do anything with that, or just leave it like this and just go with it? Right, the sine theta went to here, then subtract. Sine to here, sine squared, subtract. I just rearranged them a little bit. Where's the tangent horizontal? That's where the top is 0, right? So you set cosine theta plus 2 cosine theta sine theta equal to 0. You can factor out a cosine. And now you have to figure out where these two things are 0. So I'll have to do that on my next page. So I want to know where cosine theta equals 0. I want to know where 1 plus 2 sine theta is 0. How about cosine theta 0? Or 3 pi over 2, right? So we have an infinite number of solutions. We did something like that previously. This one, maybe move some stuff around. Sine theta is negative 1/2, so I subtracted 1 divided by 2. Where is your sine negative 1/2? At what angle? So sine is your y-coordinate. That happens here and here. There are 2 places where your y-coordinate's negative 1/2. Those are them. Y'all agree? The one on the left side, that's 7 pi over 6. The angle here is 7 pi over 6. And this one is 11 pi over 6. But you cannot jump around. Like, you can't go out to this one and then add a rotation to get to this, and then the same rotation to get back and back and back. So you have to do each of these individually. So one of them would be theta is 7 pi over 6 plus 2 pi k. So that means You start here and then come all the way back around to it. You add a full rotation, full rotation, full rotation. Or you could have the 11 pi over 6 and add a full rotation, 2 pi k, to get back. So you have lots of answers. Questions? Can you give me I know I didn't ask for this, but give me one point, one polar point where tangent is horizontal. I mean, you've told me where it's happening, right? But give me an actual polar point that's on this cardioid. So how about we just use this one right here, pi over 2, right? When theta is pi over 2. So when theta is pi over 2, can you tell me what r is? So you go to your curve, right? 1 plus sine pi over 2. 1 plus sine of pi over 2 is going to be 2. So what's the polar point? 2 pi over 2. Yes? That's your polar point. The r and then the theta. So if we go here to the cardioid, pi over 2, right, is rotate by pi over 2, walk out how far? 2, and we're up here. And look, if you go there, don't you have a horizontal tangent line? Yes? But there's some other places, right? Down here and down here. And those two come from those other two sets of solutions we had, don't we? Don't they? Understand how this is working? Could you give me that point in Cartesian? You would have to convert the polar to Cartesian, but you could also just look, couldn't you? In this case, it would just be the point, what, 0, 2? But you could, if it wasn't that easy, convert it to Cartesian. All right, what about vertical? Where do we have vertical tangent lines? Well, that's where we're going to have some division by 0, right? Vertical tangent. Does it look like from our picture that we're going to have it? Yeah, it looks like right here at this little like cusp where they come together, right? That would be a vertical tangent in there. It looks like. Let's see. We have to set the denominator equal to 0, which was this one, right? Set that to 0. Cosine squared minus sine squared minus sine. If it hasn't been too long since you took pre-cal, this was one of the main things in pre-cal that you want to be able to do, solve trigonometric equations. So that's why we kind of do it in pre-cal. Any ideas on how to solve this? Turn the cosine into 1 minus sine squared. You want to do that? Okay, 1 minus sine squared theta minus sine squared theta minus sine theta. And that's just because we want to get, we're trying to get everything in terms of sine possibly. Let's see if this works. What now? Combine all our like terms. 2 sine squared theta plus sine theta minus 1 equals 0. So what did I do there? I converted and then I moved everything over to the other side because I didn't like the negatives, or the negative on the sine square term. You all okay with that? Can you do anything with that? It's a quadratic in form, right? Does it factor? Can you factor this? I'm hoping for the best here. 2 sine theta, maybe a 1 here, a negative 1 here. Does that work? I think it does. 2 sine theta times sine theta is 2 sine squared theta. 2 sine theta times 1 is 2 sine theta. Negative 1 times sine theta is negative sine theta. So you put the 2 sine theta minus sine theta, it gives you a single sine theta. Negative 1 times 1 gives you negative 1. So that works. Now you set both of these equal to 0. You should get sine theta is a half. Yes, a half. The other one is sine theta is negative 1. Where's sine theta 1/2? Here and here. Where's sine theta negative 1? Straight down. So it looks like we have 3 sets of solutions. Theta, theta, theta. First one, pi over 6 plus 2 pi k. Next one, 5 pi over 6 plus 2 pi k. And then, what? 3 pi over 2 plus 2 pi k. Y'all understand what I did here? I mean, I'm kind of like just piggybacking on what we've already done. Does it make sense on our cardioid that we're going to have 3 different places? Yeah, I kind of, when we looked at the picture a little while ago, I didn't mention the ones on the sides. But it looks like over here somewhere we've got a vertical tangent line. And over here on this side we've got a vertical tangent line, right? So we should have 1 set from over there, 1 set from over there, and then a 3rd set from this. And that's what we've got. 3 sets of solutions. Okay? All right, boy, we have lots of time. Good, we can talk about the final. Before, though, how many of you have to take Cal 3 or are going to take Cal 3? Any? See? Okay. I like to try, if I can, at the very beginning or very end of a class to kind of give you an idea of like where you're headed, okay, if you're going to take Cal 3. So this is just kind of a very quick preview of what you do. The very beginning of Cal 3 introduces you to 3-dimensional space. So you go from a plane to a 3-dimensional space, right? And then you have now points that live in 3-dimensional space instead of 2-dimensional space. So you just get familiar with what that is. Get the right-hand rule that you learn. You learn that there are, instead of 4 quadrants, you learn that there are 8 octants in 3-dimensional space. Those are the first 4, and then the next 4 below. So you just learn a little bit about 3-dimensional space to begin. Do some other applications. What's the equation of a sphere in 3-dimensional space? All right. Then from there you go on to vectors, and you learn about vectors in 3-dimensional space, this thing dot product, cross product. And then you get to equations of lines and planes. This is a very important section. It's pretty challenging. You realize, or you're taught that you can draw lines using a different notation, a vector form of a line. And you take a lot of time to develop this. And then once you get past what a line is in 3-dimensional space, you look at what planes look like in 3-dimensional space. You know, and what is the equation of a plane? Then you're given problems like This is a very challenging problem, actually. Find the shortest distance between a point and a line in three-dimensional space. So you have a line. Let's say you have a line that's connecting, my mouse to the projector. And then you have a point somewhere in this room, like the edge of that table. What's the shortest distance between that line and that point? That's a very difficult thing to do without the whole construction of vectors and cross product, dot product, all this stuff. So you spend time on that. Once you get past that, you get to, I'm just looking at the highlights here. 10, 8, 7. Then you start to get to what are called vector curves or space curves. And so now what you have is you're drawing things in three-dimensional space. So there's like a coil, right? And the equation for this coil, you'll notice, it has 1, 2, 3 pieces to it. And each one of those pieces is called a parametric equation. So like we did this just a second ago, where x was some function of t, y was some function of t. What you'll have is now x and y and z. You'll have a third component. And you'll be using vectors instead of ordered pairs, and so it'll be a little different. But it really allows you to get out there and start to draw some really cool things like this. And of course, you'll want to find derivatives and everything else, and try and figure out if there's a fly traveling in this curve through three-dimensional space at every point in time, like what is its speed, what is its direction? That's what the derivative will give you. Then you have a problem like this. This one's really interesting. I'm sorry if I'm boring you. Give me like another 5-10 minutes, okay? You have two cylinders, right? They intersect each other. And what you'd like to figure out is, see the intersection? I just brought it in with blue. Do you see that? Take this out of here completely. These are two three-dimensional curves, aren't they? Can you come up with the equation for that curve? If you can, you're actually be able to compute its length later. And so you could actually, if you were manufacturing these huge pipes that you're going to connect together, you've got to weld them together along that curve. You can compute the length of the weld, right? How much welding material you'll need. I mean, there's just so many different things you could do with it, but it's the question of can you? In Cal 3, you actually can show that you can find the length of that curve. And then this just shows like you can use computers to draw. I use computers in all my lectures in Cal 3 because it's all three-dimensional, but this is just showing you like some really cool looking curves. This is a trefoil knot. It's a curve that ties a knot in itself. Okay, and then this is where you get onto the derivative stuff. And yeah, I won't get too much more into that. So you do these that's all vector stuff. Then you move into chapter 11. And you realize now in chapter 11 that you can start looking at functions. And I don't know if you remember when I went on the board and I drew, like you can have functions that take a number to a number, or one input, two outputs. This is where you look at surfaces, which is where you have two inputs, one output. So the idea is that the ground is x and y, and then the z is the height. And so you start plugging in points. For every x and y, you have a height. If you start putting all those heights together, you start to generate this thing that looks like a surface. Do y'all kind of see it? Yes? Okay. And from there, you start to talk about, if you have a surface, then you can go to a point on that surface and start, like, imagine standing on that point and looking and pointing in that direction, saying, hey, how steep is that ascent up the surface? Or which way should I point that would point me in the steepest direction? Or what if I wanted to walk along this surface but never change the height? Is there a way I could walk around? Think about like you have a mountain, right? You're standing on a mountain. you can point in a certain direction to go the steepest way up that mountain, but maybe there's a path around the mountain where you don't ever go up and down. You just kind of go around the mountain. So like a contour line. But this is where you actually start investigating the surfaces. Yeah, blah, blah, blah. Okay. 2, 3, 11, 6. Where are my pictures? There it is. This is one of my favorite animations. So this is a surface. I don't know if you can tell that that's a surface. Can you all see it? And I have a point on that surface, which I'm going to move because it's hard to see it. Move it over here to this side so you can see it. Get over here. There. Okay, so there's a point on that surface, right? And what we'll do is we'll imagine coming in and cutting it with a plane. Okay, so do you see that plane is slicing through the surface? That plane appears to be running parallel to this axis. Then if we look at it that way, and we take the surface out of it completely, and just look at where we intersected, and look at it from the side, then it would be very simple for us to kind of get the concept of finding a tangent line to that, right? That's a Cal 1 problem. But I could have also come in here and bring the surface back in. Let me rotate it around again. Instead of cutting it that way, there we go, I cut it parallel to the other axis. Yes? And if I do it parallel to the other axis, then I can look at it from the side again and do the same thing. I know it's probably making you dizzy flipping that around. But imagine then at that point, you have 2 tangent lines, one in one direction, one in the other, like this, let's just say. Those 2 tangent lines form a plane, don't they? This line and this line form a plane. Imagine a sheet that extends through those. And so what you have on a surface, instead of having a tangent line, you have a tangent plane. Basketball with a piece of paper on top. It's this plane that is always tangent to the surface. And you're interested in that in a class like this. All right, so hang tight. Then chapter 12, you start to do integration. So double integrals. And what I wanted you to see was, they're called double integrals. If you have a surface and you try and look at the volume underneath the surface instead of the area, then what you do is approximate it with a bunch of boxes, right? 3-dimensional boxes, and you add up all those volumes. We know that when you add them all up, you get an integral, right? But you have to go in each direction. You have to go, like the direction from here to here is one integral, adding up these, and then you have to go from here to here and add them up that way, so you get what's called a double integral. And that's the development of it. There's Riemann sum stuff in there. And so here's a surface. Why am I getting a red? I don't know. Here's a surface, right? I don't like this red. There's a surface. I'm looking below the surface and above that square. You see that square on the ground? If I just look from that square up to the surface, I'm trying to find that volume right in there. This is the one I wanted you to see. Double integrals in polar coordinates. So the idea is exactly the same as what I just said. But look at this right here. See on the ground, on the previous problem I had a square, right? In this problem I have this weird looking like circle that's been cut in half, and they're like a disc that's been cut in half, take a hole out of the center, right? And I have a surface above it. Here's my surface above it. And we want to know the volume below that. That's that curve right there is just the image of the boundary of this thing up to the surface. So that solid is this piece in here, and let me just take all this other crap out of here. So you see that solid right there? What is its volume? But to do it, you have to convert to polar coordinates, because this right here in polar coordinates is very simple. Think about this region right here. What can you tell me about all the points that live in this region? The radius of every point is between where and where? 1 and 2, right? And the angle, all your thetas are between what? 0 and pi. It's very easy to define that region. Your radius is always between 1 and 2. Your angle is between 0 and pi. Done. Very simple. Much harder to define that region in Cartesian coordinates. So we convert it to polar, and then we do the double integral. We learn later that it causes quite a bit of an issue, but we resolve it. And then you can do a problem like this, which is a great problem. You have a sphere, right? And you're going to drill out a hole from the sphere, but it's not going to be right down the center. It's going to be offset. See how it's offset? You drill that hole out. What's the volume of the sphere that's left? That's really complicated, because this cylinder, right, imagine that cylinder is like the drill bit going through. You know, it takes off, what it cuts out of that has kind of like a, I think I have it in here, let me see. Take the sphere out. Take the cylinder out. That's the part that we take out of it. Sorry if I'm killing you with boredom here. That's the part that we take out. And I don't know if you can tell, but you know, the top of it has a little bit of a curve to it, doesn't it? I mean, this is not as simple as just a cylinder with just, you know, cutting flat pieces off the top. It's complicated. It has a little cap. So you have to account for that. And believe it or not, this double integral in polar coordinates makes it really, really simple to do. I will also point out that this circle right here, this offset circle, we just did one of those, didn't we? 2 cosine theta was a circle that was offset. It's exactly how we would approach that. We would find the polar curve that represents this offset circle, 2 cosine theta, and then we'd be able to set up the whole integral. Then you go from double integrals, you go to triple integrals. Oh, that's applications. Applications of double integrals are like centers of mass of non-homogeneous surfaces, density, total electric charge on a lamina, things like that. 12.5, this is where you get into the triple integral. So now what you're doing, this becomes very difficult to understand, because you actually have a function that lives in 4-dimensional space, and you're trying to figure out the volume under it, and that doesn't make a lot of sense. So we have trouble with it, but we have examples that kind of clarify things. Multiple integrals. And then the very end of it is vector calculus, and that's where you get into things. I'll just go to the very end. Something that you may have heard of before, Stokes' theorem. Anyone here ever heard of flux? Flux? No? Physics people? Flux? You see Chrome divergence 13.5. I promise this will be the last thing I show you. Promise. All right. So if you have fluid flowing, right? Imagine you have fluid flowing or an electric field or something like that. At every point, the particle at that point wants to move in a certain direction, right? So the length of these arrows or the boldness of these arrows represent the speed at which the point is wanting to move. So you can tell that everything in this flow wants to go downward, right? But towards the edges, it's moving faster. So if you can imagine a point sitting there, a little molecule of water or something, then that molecule, the molecules on the, let's say, left side of it, if it's looking down, are moving faster than the ones on the right. So if that little molecule had little paddle wheels, what would be happening is that it would have a spin to it, wouldn't it? That molecule would actually be spinning because the things to the left of it are rubbing it this way faster than these. Does that make sense? And so it has this curl. And that's what this is. We have a way of measuring that curl. And the paddle wheel here, if I play this, shows you as I move throughout this which direction that rotation is in. So if I move this to the center, what's going to happen right in the center? What's going to happen? I don't know if I can get it in the center. What should happen right in the center if I can get it there? I don't think I can. Close enough. Both sides are the same, right, on both sides, so there's going to be no curl to it, right? Now, I couldn't get it centered. That's why it is curling slowly. You see that? If I move it further to the left, what's going to happen? It's going to curl the other way. It's going to spin that way. So I have this animation made where if the curl, which is being computed by the computer, if the curl is positive, then it rotates counterclockwise. If the curl is negative, then it rotates clockwise. Understand? You can change what's happening. You can change the actual field itself and how things are moving, and then that will also change the rotation. In this particular field, notice that if I move around in this field, notice that the curl is always 0. Do you see that? So whenever we have a curl that's always 0, it's a certain special type of field. Now imagine taking that whole idea and extending it to a 3-dimensional space. So instead you have a point sitting in 3-dimensional space and you got all this crap everywhere around it moving around. There's the crap moving around. Then that little thing is wanting to curl in a certain direction also. And so we have a way of computing that. I said last section. I promise I won't bring another section up. Then after that, you get what's called divergence. And this one, I think, is one of the coolest ones. This is what flux is. So imagine that you have this, again, you can say electromagnetic field or something like that. Gravity is another example. Or again, fluid flowing. And you look at one little, particle. And there's stuff going in and there's stuff coming out. There's flow into it and there's flow out of it. And what you want to do is try and be able to compute the net flow, the total flow. Is there more flowing out than flowing in? And that's called divergence. And this right here is an animation that shows, it computes all the stuff coming out and all the stuff going in. The red is the stuff going in, the green is the stuff going out. And I think it's kind of clear that there's more stuff coming out than there is going in. And so the divergence, if you were to compute it mathematically, is a positive number. If you change the position in the field, you move the point around, then the divergence might be negative, which there's more going in than out. So if you're at a point where you have more going in than going out, that's called a sink. And if you have more going out than going in, it's called a source. And then if you have a point where it's equal in and equal out, it's called, that point is said to be incompressible. Because it's equal in and out, so you can't, I don't know if that makes sense, can't compress it. Okay. All right, so you use that in physics to figure out what the flux is, the total net electric flow through something. All right, that's it. So one of the main reasons I like to show you this, do you see how much of that was 3D animation? Okay, so Cal 3 can be a very pleasant experience, or it can be a really, really crummy experience, depending on how it's presented. I would hope with today's technology that you'll see it in a way where they really bring out the 3D stuff, because it makes it more interesting, in my opinion. The math in the Cal 3, the actual stuff you do mathematically by hand, isn't that bad. But it's understanding what you're doing is more important. All right, well, let's talk final. We're taking a final on Thursday. That's the only thing we're doing on Thursday. I'm going to send out a review of what you should look at for the final, but I'm not going to do it until later today because we have one student who's taking the final early today. So I'm going to, it's kind of pointless for me. I don't want to show it now because that's what I'm going to use for that final for that student, so I can't show it. All right, so I will send it later, but I will talk about what it is, okay? Let's just talk about it. So you have something to write with? What the heck is that? All right. So the final things to expect, all right? Now, as far as past material, the only thing that I want you to be able to do is find a volume using washers or shelves. So you do need to be able to do one of those problems where, hey, here's a region, rotate it about this, find the volume, and compute it the whole way, all right? Not just set up, compute the whole thing. Convert series into sigma notation. So that would mean I give you a series written out, this plus this plus this plus this. You recognize the pattern and you rewrite it in sigma notation. Understand? Okay. I want you to be able to find a sum of a series. What time do we go to? 12:30? Okay, I need to speed it up. And I already told you about this. If I tell you find sum, that's going to mean it's probably what? Geometric or telescopic, right? And I'm not telling you one of each of these. These are the things you should be able to do, all right? Test a series for convergence or divergence. So I give you a series, ask you, does it converge or diverge? You go through that process of saying, oh, I'm going to use comparison tests. Here's what I'm comparing it to. You draw your conclusions. You write everything out very logically so that it makes sense, right? If the test fails, you say it failed, and then you move on to the next one. The next topic, find the R and I, which would be the radius of convergence and the interval of convergence. And I told you in class that this is something that I really like to put on tests because there's a lot that could be involved in that, especially when you're trying to find I. You have to test the endpoints, and usually testing the endpoints is really going to include some of this stuff, right? Testing the series. So those are great problems. Next thing, find or given a function f of x, find power series. And most likely this will include this thing. That was the one I gave you all the quiz on. Remember I gave you a quiz, I wrote it down over there, and a lot of people had trouble on that, but I give you a function, you go, ah, that looks like this, I just have to massage it and make it look like exactly that, and then I can do it, and okay. Next one. Well, I should say on this one, you could use that formula. Just also remember the differentiation and integration. So I gave you a couple of examples where we looked at it and we said, okay, that's not that formula, but what I'm given is the derivative of that formula, or what I'm given is the antiderivative of that formula, and then you had to like mess with it a little bit, all right? So just be prepared for that sort of thing. Next one, find Maclaurin series. Without using the table. And remember I said I would provide you the table, right? I will provide you the table of the common Maclaurin series. This one says find the Maclaurin series without using the table. So that means you have to use the formula sum, right, n equals 0 to infinity, the nth derivative at a over n factorial x minus a to the n. What's that? With a being 0, yes. If it says Maclaurin, okay? So that formula I won't provide you. So everyone's going to have that one hardwired, at least for that day, have it hardwired. The power series, the way to get it. Then something like write first few terms of some function f of x using the table. So I did examples of this where I gave you a function and it actually turned out to be like the product of two functions, and then you use the Maclaurin series and then you multiply out, you get what the first two or first few look like. You could also have division in this, like you had long division. Didn't I ask you to go do one on your own to verify something? I don't remember. Whatever. We did it. I showed you the grumpy old professor, right? You should be able to do both products and division of series. All right, how about the next thing? Sketch parametric curve. Find where tangent is what, equal to a number maybe, or horizontal, or vertical, right? I mean, if I tell you where is it horizontal, you're setting it equal to 0. If I say where is the tangent line 2, you're setting it equal to 2. If I say where is it vertical, you're going to say where's the bottom 0, right? Where do you get division by 0? The sketching part of it, again, I'll make something that you can do by hand, but that I encourage you to use a calculator for. So I want a decent picture of it. What's the next thing? All right, so the next one would be, we did derivative. How about parametric? I'm just going to say para area, a parametric arc length. That's good enough for parametric. And then the last thing would be polar. And for polar, I mean, there could be a lot of things. I could ask you, you know, convert from Cartesian to polar, from polar to Cartesian. Points, just single points. I could say draw this polar curve. Take the derivative, right? This stuff is so like fresh to us, this whole thing, like from here on, that I would just say do what I told you to do, to look at in your homework, right? I mean, if you just look at the homework problems for that, you should be okay. Did I give anything for polar, though? I didn't. I'll give you a little something to look at so you can have a reference. Y'all ready to get out of here? Okay, so for the polar section, you should look at page 522. You know, something like 3, 5. I like things like 7 and 9. We didn't really talk about those, but I think you can figure them out. '51, '53. So these first couple here are just like understanding like how the polar and Cartesian work. The last two are just derivatives. Okay, I think that's it. Do you all have any questions? How are we going to compute the grade? How am I going to compute your grade? So because we're not taking the third exam, right? So let me put together, I'm going to put together this spreadsheet of how I'm going to do it. And then when you come in to take the exam, I'll tell you all on Thursday how it is that I'm going to break it down. I've talked to some of you about it, right? Right? It's basically I'm going to work out what's best, what works out best for you. I'm either going to count one of your previous exams as your third exam, the better of your previous exams, or if your final is your best grade, it will replace your third exam. One, you know, whichever works best for you. So if you have one decent grade in a previous exam, it can replace your third one. All right, well, have a good one. I'll see you on Thursday.